He is a senior product manager geosynthetics at Naue, large German geosynthetics
Would you
manufacturer.
have this?
He has studied civil engineering and obtained his master degree at the University of Augsburg in Germany. And for more than 35
one is
years, he has been an active member.
Advance, go back.
For 35 years, he has been an active member of various associations, such as DIN, ASTM, CEN, and ISO. And currently, Kent also lectures geosynthetics in 2 German universities. At Naue, he now focuses on the future education in geosynthetics. So I would like to invite you on the floor, and you will tell us about sustainable applications of geosynthetics in hydraulic engineering.
Thank you very much for your kind introduction. It's going to be about the same what you just heard from Jorge, the result. I think we all know that in the meantime, that CO2, energy consumption, that we're good with geosynthetics in that regard. We know that. The question is we have to ask ourselves, and that's something for the next generations, how do we get that into specifications? I mean, what does it matter if we're good at showing how sustainable we are, how much cost savings we have, all those issues, if it's not specified, if we don't have an advantage in that? That's one major part I think we're going to have for the future. So I'm going to be talking about hydraulic engineering. I'm going to go through and going to show you some interesting things at the beginning and at the end, not meaning that in between is not so important, but I'm going to try to drive you in the direction and show you how we work with geosynthetics, mainly concentrated on GCLs, but there's other geosynthetics involved as well, but I can't cover them all. This is about the topics I'm talking about. I'm going to show you what's happening in Europe on CEN level. I think this is very important. Most of you maybe know this already, especially I know the Dutch are very involved in this as well. Then I'll talk about the ISO guide and then applications and how do we get to this situation? I mean, it's an interesting thing right now is we all think it's raining more, we have more water and everything, but that's not quite true. But we'll talk about that a bit later. And then at the end, of course, I'll come to the sustainable part. I'll add one other sustainable point in my whole presentation. I'll mention at the beginning, I didn't want to mention at the beginning, I'll do it, is time. With geosynthetics, we can save time as well. That's sustainable as well. We can do something with our time. Again, we'll never see that it's going to be in a specification. So let's start and see what's happening at European level at the moment. And I think the people involved, North American people might not know that in detail, but again, for the European, I think they're very much involved in that. We have the CE marking in Europe, so that all countries have the same product declaration. But the European Commission changed a few things and brought up a few issues which we have to add, and that's basically what you see on this slide over here. So we have to, in future, to get a CE marking, have 4 major topics in the CE marking, and that's release of dangerous substances. That's nothing new. We worked on that already years ago. That's not new, but the new thing is environmental performance will be one topic, very important one, basically just what Jorge just showed you. That's about one part of it. It's going to be circular economy, recycling material, plastic material being recycled after construction. That's a brand new topic, and we're not going to get that solved. I mean, I'm retired in the meantime now. I'm still working in this committee as a chair, and we know that it's not going to happen in the next 5 to 6 years. So this is a process the young generation is going to have in maybe years after that, and it's going to follow us a long time. And then the potential release of microplastics. This is a big point. I mean, we're all scared about that. Microplastics, ooh, dangerous. What is that? But one German authority said, for example, no filter geotextiles in hydraulic engineering anymore, because the geosynthetics, it gets abrasion with the rocks, it could go into the water. Of course it can. We know that. So what did they do? They said, okay, well, let's step back from geosynthetics. Let's use sand again as a filter layer. Okay, fine. So sand doesn't have any microplastics, that's clear. But what about the trucks bringing them there? they will produce more microplastic with abrasion from brakes and rubber and catalysts and whatever they have than the geosynthetics will ever do in the whole life. People forget that. So we just can't just look at one part, we have to look at the global story of all those things. For the young people listening here who are new in geosynthetics, that's why we have this guideline. This is nothing we are approaching for educated people, for engineers who are working in the industry already 10, 20, 30 years, something in that range. They don't need this guide. They know about that. But this guide was done for the newcomers, the people coming in there who never designed anything, don't know about that, and helping them work through the whole thing. And it's a working document. It's a living document. It's going to be improved. Currently, they're also talking about sustainability and things like that. So the next document published will have that in there as well, but it gives them a guide. And again, I don't want to say it's kindergarten what you see on this page. It basically is, because we all know who designed already. You have to know the application, you have to know the design life, you have to know what products you're using, you have to know about a lifetime, and then you have to do a specification, and then you know how to install it. We all know that. But for somebody who doesn't know that, this guideline, especially for the barriers, is built up totally different than the others. It's giving you questions. It's like, yeah, think about this, think about durability. Look at this plastic material against that geosynthetic material, have a look at that. And you see it's number 9, so there's, I think there's 11 different documents in there, which are really good, and they're coming out constantly. So young people, look into that, get a copy of that. Water. I recall in the 90s, we were all thinking we're gonna run out of oil. I think you heard about that, right? And they told us, 50 more years and then we will have no oil anymore. You know, we were scared. In Germany, we had Sundays no traffic to save oil and all that stuff. But a professor a few years later at university told me, we're not going to be fighting oil in future, it's going to be water. Water is the issue. And he's right. Because if we don't drink water, we can't drink oil. We won't survive drinking oil, but we need water to drink. And there's a lot of stress situations we have because of the global warming. What Suzanne said at the beginning, the global warming is creating a total different site of the world map in regards of water stress. And you can see what's happening over here, that North America is red. You're running out of water. I mean, if you're living on Lake Michigan, you're lucky, there's a lot of water, but Texas and that area, there's no water, hardly any water. So that's going to be the issue we're going to have in future, and you can see in the middle, where in the past we always thought we're safe in Europe, in that hemisphere, we're safe, we will always have a lot of water. No, that is changing, and water is the big issue which we're talking about. Water, or our rainfall, is getting unpredictable as well. And look at this nice graphic. It's similar to, I'm comparing decades back to decades, the last decades we had, and what happened? Well, what happened is the intensity of the rainfall changed dramatically. So you can see on the left side, you can see that the millimeters per day, the low numbers, they are decreasing, but we're increasing a higher intensity on the strong rainfall days. What does that basically mean? The problem is we all think the rainfall is equivalent or is growing or is falling down. We'll come to that on the next slide. That's not the issue. But the problem we really have is, which we have to understand, is we have dry summers like we had in the last years in Germany and in Europe. If we have dry summers, then the soil is dry. And if it now rains very intense, everybody thinks, oh, great, the water's going to suck up in the soil and it's going to go. No, it doesn't. It just runs off. A dry soil is like a barrier, allows the water to run off, and the consequences are these things we see every year somewhere. Every year you can go in a different country, you will see pictures like this. Okay, it's dramatic, I know, but that's what my presentations are like. They have to be dramatic so I can get into motion and really get into the topic. And then things like this happen. Hydraulic engineering, the areas we protect are not protected anymore because now suddenly, and the dams don't last anymore. What's the cause of that? We see that in Australia, we see that every year in some other place, we hear it. It's in Spain, it's in Italy, it's wherever, I'm not sure. In Netherlands, probably not that much, but also you have a different concept, but you have dikes as well here. And the issue on all of these dikes, it's all the same, that many of these are very old. They're built hundreds of years, 50 years ago. Sand. Obviously, if animals are in there, they dig holes in there. Water flows through there. We have longer, drier summers. They desiccate, and they're not safe anymore. Water goes through. They crack the levees. We have roots in there. The roots, if the plants die because it's hot, the water flows through where the roots were. All these consequences. I'm not even talking about the height of these dikes. They're not high enough anymore. If the water in the ocean, if it keeps on rising, which it will, then we're first the Dutch, then Germany, but but that's it. You're lower than we are, but we're in trouble as well. The water's going to find its way. And that is an issue we have. We have heavier rainfalls, and the most big part of this is the rainfalls sometimes are longer, the water lasts more. These dikes and levees we built years ago, they were about to last 5 days, maybe maximum 10 days. We don't have that anymore. We have them 20 days where the water's standing there. And then suddenly the design, there it is, longer exposure to water, the design is suddenly totally different. And the last one is going to be interesting as well on the slides over here. Well, I love this example because the Merrimack River flood, they had the same problem. So on the top side, let's see if I can deal with this. There we go. Nope, not really. There we go. Somewhere. Is it? There we go. In that area, this area, they knew that they're going to have rainfalls, and they said, oh, let's build good dikes, better dikes, higher dikes, and make our area safe. Fantastic. It worked. It rained, and they were in good shape because they put the dikes where they really shouldn't be, because this area over here, basically in the past, was for the water of the dikes to collect if they have a flood, that the water can flow in there and slow down. But now it's industrial area. There's housing in there, so they put the rivers, what I just told to you a few seconds earlier, they put them directly on the riverside and made high dikes so they would be safe. And they were safe. But the water's running downhill, went to the next area, to the next town a little further down and flooded them. Because all that water couldn't stand up there, it went down and they got flooded. So flood protection can only be done if all of the communities work together, and if you don't do exactly this, what was done in that area. And this is the reason for this. It's a nice comic. I love this comic. In early days, we all had that even in Germany. The same thing over here. These areas, there was a lot of water which could be stored there. Building was not allowed to be done in that area. So if there was a flood, the water could flow there, it could expand, no problem, no issues. But then suddenly we're growing, more industry, more people want to live closer to the water. They said, oh, let's build a dike. If we have a dike, we're safe, and then we can sell that property, build housing areas, get good money out of it. And then we start selling that material, build housing areas, build up the dikes. But they didn't know, and that's the same thing we have today. We're not going to know what's going to happen in 20 years. We don't know that. I don't have a glass bowl. I cannot tell you what the rain intensity is going to be in 20 or 30 years. It can change in one direction or the other direction. I doubt it will. But if then suddenly we have more water, longer lasting water, if we have melting water from the mountains plus a storm, plus rainfall, well, then these things happen, and then suddenly those nice areas over here are flooded with water, and then we have the disaster areas over there. Okay, I'll skip that one. This is like just one area in Germany. It's in Berlin. I like this graphic very much. You don't really, you can identify anything out of this graphic. You can make your assumption whatever you want with this type of graphic. But if you look at a trend, a linear trend in it, you can see that we have an increased rainfall over the years. Now, what does that mean? Again, a smart professor told me that. It's not what I found out in any research or anything like that. If the temperature increases by 1 degree centigrade, what does that mean for us in Europe? Does anybody really know what that means? Increase of 1 degree? 1 degree temperature increase is about 10% more rain. We all think it gets hot and less rain. No, we have evaporation. The water has to go somewhere, and it will come down somewhere. In Germany, sorry if I keep on saying Germany, but I just know that from the news, since September last year to about April last year, it just rained every day, nearly. It was wet, it was raining, it was raining. The years before, it was dry. But that's normal because we don't know where is that going to. We're influenced by the Atlantic, by different types of oceans, by weather temperatures, how they move, how the highs and the lows are. And sometimes it falls down in Spain, sometimes in Italy, and this year it hit Germany. We're wet, we're underwater. And those things are, what I meant is we don't know, there's nothing predictable. So let's look at hydraulic engineering, let's look at the levees, what's going to happen. And these are cases, what's going to happen if it rains a lot, what's going to happen with the dams or the levees. And the causes are, if we have overflow, that's the worst case scenario. If we have an overflow, you can really just reconstruct the whole dam. Talking about roads, that's a good thing. I like your 1,600 times around the earth. I'm going to do that with coastlines, and I'm going to do that with dams in the world as well. And I think we're going to be close to your numbers of roads as well. I think we have a lot of rivers in the world and a lot of dams. So if those overflow, they have to be rebuilt. The problem there is not like a road construction. If you have a hole here, you can repair it. If a dam is overflooded, it's going to be over miles, in your language, kilometers in my language. It's going to be a lot of kilometers of which material which has to be repaired. If you have a lot of flooding on the water side, you don't see if there's going to be erosion or not. That's a big problem. That's not, you don't know, is the dam going to break or not going to break. The next one is the underflow underneath. That one you can see because on the off-water side, you can see water coming through, but the erosion through the dam is also very crucial. You shouldn't have water going through. These dams are typically just sand dams in the past. That's not going to work anymore. I can tell you that right now. So there's a three-zone levee concept in Germany, which if you look at the year when that was written, it was in 1986, the first time introduced. The issue on this thing is it's only a recommendation. A recommendation is not strong enough. It's state of the art. It's okay, you could do that if you want. You need regulations to get these things really built. And the concept of this three-zone dike is very easy. You have a barrier on one side. So you have a barrier on the upstream side. Then you have, of course, a stable construction in between. This one can be done with geotextiles, with geogrids, with all types of materials. You can have even drainage materials in there. You have to make it stable. That's the important part, because if that material flows, it will go. So reinforcing or putting them in sandbags or whatever construction you want to have would be a good idea to support it. And the most important part is to have on the downstream side, have a road construction, have, as we call it, a dike defense road. Because typically these dikes are not built in areas when it's wet, you can drive with your vehicles around, but if you have a dike defense road, you can quickly get to the construction site. And if you have a failure, you can start putting in sandbags and reinforcing that area and do something. And it's also nice for the cyclists, bicycle drivers to drive around on those dikes. And of course, here are a lot of geosynthetics involved as well, but again, geogrids, geotextiles, whatever materials, but I won't go too deep into that. We can run calculations, universities do that, you can do that, but at the end of the game is a calculation is a calculation, it makes assumptions. It's a top one is without one, you can see how the flow through is going through fairly quickly. The real question we always have, how long is the water going to stand on that side? I don't have the answer for that, but we do know today it's sometimes more than just the 5 days we predicted 50 years ago. You have to calculate, you have to put safety factors in there, and basically then run your calculations and see what's going to happen if you put a barrier type in there. Basically, we know that it can withstand the water for hundreds of days, and we're not going to have floods like that in hundreds of days. Now, there was one really good guy. And there are many good guys in the world, but this was a really good guy. Dr. Krüger, he came from Brandenburg. He said, I'm sick and tired of this. You know, in my country or my state, everybody builds how they want to do it. I'm going to write a regulation. And I say, I want geosynthetics in there. I want G-cells in there. He's the first person who wrote this. And by the way, just for your information, the Dutch are working. They took this guideline and copied it, which is good. No copyright infringements on regulations like that. They took it, they discussed it, and they're taking it in their guidelines as well. You can ask Reich, I don't know what the status is where we're standing right now, but he knows about that. And that's good because they're taking experience from something which worked in one country and not renewing something and doing it on their own. And he basically took the 3-zone dike. It's maybe next time I should, so that's easier for you to get it. It's now on the other side, so the upstream side is on the right side. He's saying geosynthetic clay liner. He's not taking compacted clay liners at all. He says, I want a geosynthetic clay liner. He trusts that system. He has a lot of experience because after 1998, where they had the big floodings on the Oder in that area, they repaired a lot of dikes because they didn't have time. They knew exactly the next flood is going to be coming soon. I have to repair kilometers of dikes. I have to repair them, and you have to install quick. So sustainable on time in that regard to get more kilometers of dikes done. Same thing in the middle of the ballast area, dike defense road on the backside, and then on the bottom side, a relief wedge, basically taking the water out in case anything flows through the guidelines. I'm not going to go in technical details, but again, this guy also was thinking very rational on this whole thing. He said, I'm not going to reinvent the wheel. I want lifetime. I want 100 years lifetime. So he said, where do I get that from? Well, he went to the German law on landfills, where they had GCLs for landfill capping systems, and you have a regulation there how to calculate 100 years or what you have to do to achieve 100 times lifetimes with a geosynthetic clay liner. And he said, I'm going to copy that. Even though it's a dike application, a levee application, he took the landfill guideline and said, it's all there. Why do I have to reinvent the wheel and do something new? And I think that's a smart move, but so we're not going to go. It includes all geosynthetic clay liner types, so nothing's excluded there. That's just one point. And then again, some pictures of installation. Here you can see how they work. You know, they put the GCLs on place where they have to be installed, and then pre-prepare the area, install the GCL, put in the wedge in the front, dig it down deeply so there's no underflow under the dike, also a concern you have to be aware of in case your subgrade is not impermeable. And then basically I'm not going to go into the summary, we all know they're thinner elements, we know about that. That's something which a lot of aged engineers can't really live with. They always think, compacted clay liner, this thing must be better than just 1 centimeter geosynthetic clay liner. We'll get to that a bit later. I'll show you some examples on that, what that basically means. A big point is the resilient one. I should have mentioned that at the beginning. These designs have to be built resilient. They have to withstand nature. That's one of the most important things, because if you have a flood, it should still be standing there, it should work, and should not be damaged during that part of the time. And cost effective, of course. Here's a nice example in the Netherlands. They're also following that. Again, I don't know the exact status on the guidelines, so please ask a colleague of mine. Underwater insulation also, if you have a canal, okay, I'll go through this fairly quickly just to show you that there are some other hydraulic engineering applications as well. I mean, how do I install, if a compacted clay liner which was used in a canal, also 50 years old, how do I repair that underwater? Very, very complicated. And basically one solution was just to use the sand ballast geosynthetic clay liner, basically having a geosynthetic clay liner with sand on top of it so that it would go underwater. And if you then put your armor rock drop on top of it, it's also a protection layer additionally. So there are concepts out there, and I'll just rush through that. In the old days, we needed divers to see where they installed it. Now, in the meantime, we're much more modern. We have GPS. We know exactly where the geosynthetic clay liner or the material is laying. So that is really an improvement. Sustainable in time again, you know, it's much quicker, cost effective. And here's just another project in Bavaria, just to show you that these things has been done. Let's go to what you just saw right now is, I would say, low gradient applications. Even though you could have 4 or 5 meters of waterhead on top of the geosynthetic clay liner, now we're moving into area 20, 30 meters, storage of water. They were built in the past, typically also with compacted clay liner 50 years ago. They worked. They worked for a very long time, but you know, they have their lifetime as well. Nearly every construction we build in the world has a lifetime, and nothing lasts for 1,000 years or more. That's impossible. We always have to, engineers think about what's going to have to after that. And that's what also the CE marking is doing, you know, recycling of these geosynthetic products. Very important part, you know. We should make the people aware it's possible. We can do it. We can recycle these materials. We can reuse them. They're not going to stay in there forever, degrade, and be gone. We can do that, but we have to work on that. So here we had a failure, same thing as we had before. It rained stronger. We had a lot of water. The dam, think about that, a 30-meter high dam overflowing. I mean, you have to now start repairing the entire 30 meters, or at least part of it. And this is what happened. They had a real huge failure, and this whole material had to be replaced. Okay, so they decided to take a geosynthetic clay liner, but they weren't absolutely sure, which I understand. I mean, 30 meters waterhead, just based on a 1 centimeter clay liner, they didn't do it. They said, okay, let's put 10 kilograms of bentonite in between. Let's make it thicker. And to be absolutely sure, let's take 2 geosynthetic clay liners and put 2 in there. And to be absolutely sure, let's put a drainage layer in between and measure if anything goes through. And if you do that, we'll be confident. Okay, that's not sustainable. I think the compacted clay liner is probably economically cheaper, but they wanted to go thin and needed a quick installation. But this first application they had, they worked on that. They said, okay, we'll put 2 geosynthetic clay liners in there. And here's a cross-section in there where they said, okay, the drainage layer in between will collect the water in the middle where the clay liner was okay, and then we'll see how much water is flowing through there. Okay, end of the story was that after 5-6 years measurement, nothing went through. So they were confident that works. And here you can see just a construction site of the top 18 meters. Then they came, this was also one. So, yeah, sorry. Yeah, this is my trumpet. I like this. What you see over here is the overflow trumpet. Engineers learn. You know, they say, oh, it could happen again, this overflow. What do we do then? So they made this huge trumpet just about on the 1 meter under the water level of the maximum of the dike. And they said, if it ever comes to that case that we will have more water, it will go right through, bypass the dam, and go down into the valley. So they didn't want to have an overflow. They learn, we're smart, people, we're smart. We learn from failures, but then you have to improve it then. And I think this was a really good design, which they did. So I like this trumpet picture there, over there. Trumpet. Okay, then we have energy. We're producing a lot of energy, not the most efficient one here. The efficiency of hydro energy is not that good, so you pump up the water when the energy is cheap, and then if the energy is expensive, then you produce hydro energy. And over here, again, over here on this side, you can see that's a huge dam. Down here were housing areas, was built around about in the 50s, and obviously, they did measurements there. They had how much flow through is going through that whole system. Again, we forget these things. This is an old design you can see on the drawing, no computer drawing, hand drawing. But our fathers, our geotechnical people from decades ago, they were smart. They were really smart. We sometimes forget those things. What they did is they said the clay liner I have over here gets thicker the further down we go. And they said the waterhead divided by 5 should be the thickness of my compacted clay liner. This way the gradient is always the same. So it doesn't matter. So on the top where you only have maybe 5 meters of waterhead, your compacted clay liner is 1 meter, but 30 meters, your compacted clay liner should be at least 3 meters in thickness. Smart design. Nowadays we would make it everything 50 centimeters from the bottom to the top. That means that the weak spot is on the bottom where I have the highest gradient. I like that. This picture, I love this. I use it in university as well to tell the people, you know, look in old drawings. Sometimes they are better. We try to improve things, but this is the wrong way to go. So they had then, obviously, as you can see over here, in the 90s, they suddenly had a lot of flow through the dam. And then obviously knowing that people live downhill on the bottom side with 30 meters waterhead, you don't want to collapse. So they knew they had to do something, did investigation, and the same thing again, they had to repair this entire dam section, because they knew it was leaking everywhere, and they came up with different solutions. Of course, they had compacted clay liners, they had asphalt, they had geomembranes in there, but they did a plus-minus analysis, and then they found out fairly quickly, we don't have the time. Time is money for hydro engineering. Because if they have to build a full year, and with the geosynthetic clay liner as an example, which was a solution, they can build in a half a year, they get a half a year more energy. And that money they make is worth a lot. So they came up at the end coming with a solution because the designer was the same guy who designed what I showed you previously. He had experience, he knew it works, and now he reduced it. He just took one layer, he still put in the geosynthetic drainage material in between to do some measurements. So they only had to repair the top part because the bottom part was thick compacted clay liner and not really always had water. So they only had to fill the top layer and they repaired that one. And the design was the same as before. They used program GCL, bentonite GCL, installation of the GCL, installation of a drainage material underneath to do some measurements because that's very important in sections. So now this time they improved the design. The other design didn't have any sections, so that's why they had to repair the entire dam. Now they put sections in there and said, okay, if we have a leakage in one section, we know it's there, we only have to repair that area. And here's the bonding in the wedge again on the right side. Overall view, construction quality control, of course, installation with the cover soil always in one direction, no turning, no driving around, no stressing in there, because you could damage a thin element, so they're taking account of all those things. And this is the view of it. We're talking from back there to up front here about 1.5 to 2 kilometers, just to give you an idea of the size of this. To empty this dam, 6.5 hours. The water is, after 6.5 hours, gone. I mean, there's millions of cubic meters water in there. And then you can see the measurements afterwards. Of course, you will have a little leakage, but that was redundant. Those are just tablespoons of water. And in the meantime, nothing is going through that entire system. Let's come to the sustainability and to the end part, because I don't want Susan to stand up and give me a warning. I don't like that. I get enough warnings at home. Yeah. I'm in a trap now. That's right. Oh yeah, right. Okay, so here we're comparing, and this is the only comparison I'm doing: compacted clay liner versus a geosynthetic clay liner. You can just see on the picture already the big difference on equipment. And equipment obviously automatically is CO2, energy demand, time, and one big part is going to be water again. We're going to be talking about water. Might not be that interesting for us in Europe yet, but I know in South Africa and Australia, South America, where I did the same presentation, it was an eye-opening for many of the people. Let's start easy part. Very easy now. You know, I'm going to try to get you further. If I build a pond, 3,000 square meter pond, small pond, really something really small, not big. You know, on every highway, Autobahn, you will have one of these. And you want to build it with a compacted clay liner, you have to excavate, you have to excavate the soil and take it out. Now you have to bring that material to some place. If I run a calculation and it has to go to a landfill, we're talking about 35 euros per cubic meter. And in the meantime, that was in 2014. In 2022, the number is about double. It's about 75 euros per cubic meter depositing in a landfill. So if I run through this calculation and I take out 3,500 square meters, half a meter of clay, and bring it to a landfill, you can see the cost difference of it. We're talking about 30 to 70,000 euros more costs on 3,000 square meters. I mean, I can use a GCL easily with that cost. So depositing, excavating the material is a big time issue. Water is the next issue. This is the most important graphic for countries who don't have water. If I get compacted clay liner, the compacted clay liner is delivered at 12% moisture content. The optimum moisture content is around 18% or 14, 15, 16%, something in that area. I have to add this water during construction of compacted clay liner. Just to give you an idea, if I take an area over here, I took 40,000 square meters, half a meter in thickness. We need about 1.5 million liters of water. That doesn't mean very much. What is 1.5 million liters of water? It's a number. But if you take it down and break it down to what a person in poor country needs on water, you could supply 205 people with water per year, in 1 year. That counts in South America, Australia, in other hemispheres. Over here, not yet, but it's going to be coming. Transportation, I said that, 4,500 square meters is one truckload, 187 truckloads to get the compacted clay on site. Think about all the rubber which will go into the environment. Look at the CO2. Construction, I'll go through, leave out these slides. Same thing, energy demand. Energy is expensive in Europe, huge amounts. Just the energy we need to build GCL or compacted clay liner, and this is from the production, from mining of the bentonite to the insulation, from the mining of the clay insulation. It's a whole process similar. You took a little shape out of it. I'm taking the whole thing. You can see that we're saving 42% less energy with the geosynthetic material. Same thing with CO2 emissions. Also, 36,000 square meter size, we have around about 60% less emissions. The same graphics. I don't have to do that. Go on the EAGM site. The EAGM website has a lot of these examples, and you will see that. So I'll just skip through those advantages. I guess the presentations will be distributed. So this is just my summary of the advantages of a geosynthetic clay liner versus a compacted clay liner. 15 advantages. Some of them I didn't even touch, but they're very, very convincing. And at the end, the last picture is basically the future is green. We know that. The future is water. It's raining a lot, but we still have to protect it and conserve it. So thank you very much. And sorry that I had to rush through the last minutes.